Hello, welcome back to AC Circuit Analysis. I lied to you a little bit. I said we would work some problems right now, but actually I have a couple more things I want to tell you before we can work some problems, but you'll thank me after I'm done. Let's go ahead and talk about the idea that complex power S is equal to VRMS, because most of the time you are going to be dealing with RMS values, times I RMS conjugate. So this is what we actually learned from the last section. Let me go ahead and change colors here. But recall that the following is true. VRMS is equal to the current IRMS times whatever impedance you're flowing through. So typically you're trying to find complex power across an element. So there's some impedance here, which is a complex number. So V is equal to IZ. That's something we've been using all the time here. So then when we substitute that in, what we will get is S is equal to, for VRMS, we'll just stick this in, IRMS times the impedance Z, and then it'll be multiplied by IRMS conjugate. All we did is take this guy and stick it into what VRMS is actually equal to, if we're talking about a specific circuit element. So at the end of the day, the complex power is going to be IRMS times IRMS conjugate times Z. Now, how do we simplify this further? You have a complex number, or a phasor, called IRMS, and you're multiplying by the same exact thing, but the conjugate form of it. And how do you simplify that? And if you go back to algebra, actually I guess this is probably past algebra, whatever trig, whatever class you learn this stuff. If you have any complex number and you multiply it times its conjugate, a really interesting thing happens. You always get the magnitude of that complex number squared. That's what you actually get. You get a number back. When you take a complex number and multiply by a complex number, you get a real number back. This is the magnitude, the length of that complex number squared. And the reason it comes back that way is because of the following. If you have a complex number A plus JB, right? I'm just going to kind of give you a little refresher. And A minus JB. Okay, this guy is the complex number A. This is the complex number A but conjugated. All it means is you stick a negative sign in front of all of the J's that you see everywhere. Then what happens? You just do FOIL here. So A times A is A squared, right? And then you have these inside terms and the outside terms that you have to have in there. So you have plus JAB and you have minus JAB because the inside and the outside terms. And then the last terms that you have is going to be what you have here is you have a negative times a negative, that's a negative times positive, that's negative, but then J times J is also -1, so that those cancel out, so you end up with a positive B squared here. So again, the J times J at the end is J squared, which is -1, which cancels with the negative that you would get from the signs right there. So what ends up happening is these cancel away, and you have A squared plus B squared, which is just the magnitude of the complex number squared. In other words, if you look at that triangle here, right? So this is A and this is B. This is the real and imaginary part here. Then basically this is the magnitude of A squared, because it's like a Pythagorean theorem, right? A squared plus B squared should be the length of this side squared. So when we multiply times the conjugate, we end up getting A squared plus B squared. We end up getting the real part squared plus the imaginary part squared, which is the length of the other side squared. So all of that stuff in our back pocket. Now when we look over here, we have this current multiplied by its conjugate, and so basically what you end up with is the magnitude of IRMS squared times Z. And don't let me let you forget that when you calculate complex power, it's just P plus JQ. I'm just writing